Hi, welcome. So this is a video on Cronbach's alpha. So recently I've seen a lot of thesis students and their master using this concept that's called Cronbach's alpha, and I had no idea what this was, so I had to look it up. So this is a video on Cronbach's alpha. Right? So Cronbach's alpha is basically, it's a measure, and it's used to capture or to measure the reliability of what we call measures, or to measure the internal consistency of several measures. So let me explain. So here is an example. Let's assume that you have a survey, and a survey has a couple of questions. Here are 3 questions, and these questions try to measure something, and they all measure the same thing, right? So for example, X1 asks you, how much do you like mathematics? And X2 asks you, do you think mathematics is fun? And so on and so on. All right. So these kind of measure the same thing. And what you want to do is you want to get the common measure in all these 3 distinct measures, because all these 3 are measured with noise, and you want to capture what's common to both of them. So what do you do in practice? Well, in practice, you have a couple of variables that kind of measure the same thing. And then what you do is you take the sum of these things. So here you have several subjects answering your survey, A, B, C, D. And then for A, you sum 1 to 2 to 1, which is 4. So Y is basically the sum of all the answers to the different questions. And B is 2 plus 3 plus 2, which is 7. And then C, the sum is 9. And for D, the sum is 13. All right. And then what you do, you compute Cronbach's alpha, and here's the formula, right? So basically what's this formula? This is K divided by K minus 1, and here K is the number of questions, right? So this here in this example, it's 3, 1, 2, 3, right? So you have 3 divided by K minus 1, which is 2, and then between brackets you have 1 minus, and then here you have the sum of all the variances of all the questions xk, right? So for every question here, for x1, you compute the variance, which I've done here, which is 1.667. For x2, you compute the variance. For x3, you compute the variance, and you take the sum of these 3 things. I've done this before somewhere, so let me check, right? It's something like 4.92. And then you divide by the variance of the sum, right? The variance of 47913, which here is 14.25. And if you do this, you get the number, and here the number is 0.982, so that's my alpha. And in the literature, then they say alpha bigger than 0.7 or 0.8 is good. If it's below 0.7, then it's actually not so good. All right, that's not here the question, what actually this level should be. The question is here more like, where does this formula come from? What does this actually alpha mean in terms of mathematics, right? That's what we're going to try to answer. And then second, where does actually this formula come from? Okay. So Cronbach's alpha is a measure that there's an underlying mathematical model to this. And of course, this model depends on a number of assumptions, right? So, and the main assumption here is that the answer to question K can be written in the following way. Well, it's just a constant, right? It's common to every observation. So X is the random variable, right, which varies over the subjects. You have AK, and then you have a random variable T, and then you have an error, right? So there's like this common part T, and then there's noise, right? So you can, epsilon is the noise part. All right, so what's common here in this model is that, well, this is a fixed number, but here the T doesn't depend on K, right? For every question, this T part is the same one. And this is basically what we call tau equivalence. Tau equivalence basically means that this T, which is one-dimensional, is common to every question. And if you look at it, there's a coefficient here in front of T, and this is always equal to 1. Right? There's no difference in scale here over the different questions. So that's basically the main underlying assumption for this model. That's not an O, that's just something I indicated. Okay, there's a couple of other assumptions that need to be said. First of all, well, the mean of the noise is equal to 0. that's not really a strong assumption, because if the mean of the noise would not be 0, then you just incorporate it into this constant AK, right? So that's basically an innocuous assumption. The stronger assumption is that for different questions, so if you have two questions K and L and they're not the same, well, then the noise, the covariance between the error terms are basically 0, right? So that's second question. These noises are independent of each other. And then there's a third assumption that basically says that for any noise, for any questions EL, then the covariance with T, which is this common part here, well, that's also equal to 0, right? So the noises are uncorrelated with the common part over all the questions, right? So that's basically the three assumptions. Okay. So now going to the alpha, what is actually this alpha? Well, if we have the y, right? So remember y was just the sum over all questions of all the answers, xk. Well, what you can do, you can compute the variance. You can compute the variance of y. Well, the variance of y, that's simply the variance of the sum over all the xk's. Okay, that's an easy one. That's just the definition of y. Well, this variance is equal to the variance. Well, now given that we have our model here, what's this? Well, there's the variance of the sum over all ak plus t plus epsilon k. And now you have the variance of the sum. Okay, you have a sum of a couple of terms, and you can decompose this in the following. Well, the fixed part here drops out, right? So the variance here, any combination will be 0, but it's going to be equal to the variance of t plus, well, overall the sum of k's plus the variance over all the noises, and then of course plus the covariance over the sums of k, of t, and the noises. Okay, but basically this is just the two parts. Now, because of this here, this last part will drop out. This will be equal to 0. Okay, so basically what you have the variance of all the sum k sums of the same thing t plus the variance over all the noise terms. Okay, so you could say like this is what you want to capture, right? This is the common part. This is what's really interesting, and then you have all these noise parts. Now you can simplify a little bit because the t's are the same for every k. So this basically k, or let me go big K. There are big K questions, k times t plus the variance of all the noise terms. And now the alpha. What is the alpha? Well, it's basically how big this part here, the interesting part that you want to capture, is in comparison to what we observe, right? So alpha is basically the variance of this kt divided by the variance of y. Okay, that's the Cronbach alpha that we would like to compute. Now, if you want to compute this, well, we can compute this here. You already done it in the previous exercise, right? This was an approximation, right? It's 14.25. But what we then really want to compute is this here, right? The numerator of this fraction. Okay, and this is what we're going to do now. Subsequently, how do we compute this here? Let me remember, variance of kt. How do we? K is a fixed number, right? So it's basically k squared times the variance of t. T is the random variable here. Now, how do we compute this? It's not that difficult, right? So this is the insight. So let's take two questions, K and L, and assume that they're different, all right? So what we can do is we can compute the covariance of xk and xl. Okay, well, let's just substitute. This is the covariance. What's xk? Well, it's ak plus t plus epsilon k, and xl is al plus t plus epsilon l. All right, so this is the covariance of two sums, so we can split apart. The constant part here, ak and al, drop out. So it's the covariance of t and t plus the covariance of t and epsilon L plus the covariance of t and epsilon k plus the covariance of epsilon L and epsilon k. And now you see that this here is 0 by assumption, this one is 0 by assumption, and because L and K are different, this is also 0 by assumption. So we end up that this is equal to the variance of t. Okay, so the covariance between two questions is basically the variance of t, right? That's just derived from the underlying assumption. And now, what will we do? Well, we take the sum over all two questions that are not the same, right? So we can approximate this. We can basically take the average over all two questions that are distinct. Well, it's every time this will be an approximation of the same thing. It's the variance of t, right? And how many of these sums do we have? Well, it's k times k minus 1 of these sums. So it's k times k minus 1 times the variance of t. Okay. Now, it's not exactly what we want because we want k squared variance t. So what we can do is we can put this as k minus 1, divide by k and multiply by k is k squared variance of t. So this is k minus 1 over k times the variance of kt. All right, so what do we get? We get that the variance of kt divided by the variance of y, this was my alpha, right? Well, this is k minus 1. No, you have to bring it to the other side. It's k divided by k minus 1. And then in the numerator, we have the sum of k different from L of the covariance of xk and xl divided by the variance of y. Okay, that's our alpha. Now, we're getting somewhere, let me go back to the first page. We're getting somewhere over here, but it's not exactly the same because here we have the sum over all k of the variances and not the covariances. But we're getting there very quickly, all right? And so we only need one more thing. Well, remember that y was as the sum over all the questions, all right? So what is the variance of y? Well, it's the variance over the sum of all the xk's. And if you write this out, well, what do you get? Well, it's the sum of all the variances, plus, of course, all the covariances between the different questions that are not the same, right? Covariance xk, xl. And now basically what you do, you take this here and you substitute this out. So what is my alpha? My alpha is nothing more than k divided by k minus 1. And now this is equal to the variance of y minus this part here, the sum of the variances over all the xk's divided by the variance of y. And now the only thing left to me to do is to simplify. Here this is 1 and minus the sum of k of the variances over all the xk's divided by the variance of y. Okay, so this is how you get to the formula for Cronbach's alpha.